Okay, well, I think we should start the session. It's 9:02. We're very fortunate today to have Zsuzsa Marka to talk to us. So Zsuzsa is originally from Hungary, and then she did her PhD. She did her undergraduate degree in Hungary, and then she did her PhD at Vanderbilt University, graduating in 2002. And then she went on to do a postdoc at Caltech and UCLA, and then she joined Columbia and has been at Columbia ever since. He's now a professor and a research scientist at Columbia Astrophysics Laboratory. Zsuzsa is famous for her work in LIGO for developing the timing distribution systems, which are being used in LIGO and in Kagra. And these are, very essential of the overall operation of the interferometer. This is one of the key systems which allows us to make astrophysical measurements using this machine. But she's also been thinking a lot about, many different things. I was intrigued to learn that she's also working in a biology optics lab, but that's not what she's talking about today. She's talking today to us about the multi-messenger astrophysical multi-messenger astrophysical measurements. And this is something that Zsuzsa has been working on for many years and has made some pioneering contributions to this field and is still continuing to do innovative work. Welcome, Zsuzsa, and please tell us something interesting.
I definitely hope I will be telling you something interesting. And thank you so much for the nice introduction, Yuri, and everybody organizing CDI for inviting me to speak to you. I think these kind of meetings between, in this aspect, although I have a very strong instrumental background, but right now I'm talking to you also as a data analyst. So this getting together of people who actually analyze data in the multi-messenger sense, and people who are interested in the theory and in the sources which can emit multiple messengers, it's very important. And I will be actually begging for your help in a few requests which are necessary to move this forward, this field forward. You just quickly after 30 minutes, please give me a reminder. I tend to talk longer than I can, so I will need a reminder.
Sure, I'll send you a private message.
I hope it will show up. You can certainly stop me. Thank you so much. Okay, so multi-messenger astronomy. There are a few, definitions available. This one is from Bartosz and Kowalski, 2017, Exploration of the Universe through combining information from a multitude of cosmic messengers, electromagnetic radiation, gravitational waves, and the particle messengers, neutrinos, and of course there are cosmic rays as well. I'm not gonna go and talk about cosmic rays. We can at the end a little bit. They are very tricky in the MMA point of view, and at the end we may discuss that's why I see it that way. All right, so the energy distance scale, all these messengers, the EM messengers, which we have a very wide wavelength range and many existing observations, we can see them to large distances in the universe and fairly large energies, but then there's a given segment, as you see on this figure, which is opaque to photons. And this is where my two favorite messengers, which are gravitational waves and neutrinos, come into line. And I will actually giving most of my examples through that messenger, those two messengers. Okay, so I also have a little definition or how I'm looking at multi-messenger astrophysics from the point of view of a data analyst. And that is that we would like to connect different kinds of messengers, observation, electromagnetic, gravitational waves, or neutrinos of the same astrophysical event, be that a supernova or a binary merger, or not necessarily transient event and transient sources, but some astrophysical system which can emit on a longer scale, can be an active galaxy, say, or sometimes intermittently emit as like a soft gamma repeater. There are so many different possibilities, but it's not just there is a single event and then something happens and then we only have one chance to detect, but there are these other astrophysical systems which we can certainly look at in the multi-messenger context. I will be talking mostly on the first one, about transients, partially because in gravitational wave detectors and data analysis, I'm using transients, and that's where most of the LVK detections have been coming. That's where the LVK detections have been coming so far from. So we would like to discover new and definitely more transient and their emitting sources. But of course, we are doing an MMA search, and sometimes we just want to constrain a joint population because we have upper limits if we don't find anything in our data. But if we find something new and interesting, and this is where we need the theorist hat, we need to uncover the physics through observations to tell us about the multi-messenger emission mechanism. Okay. So this comes. Okay. All right. Okay. Sorry, it's always a problem moving my slides. So my outline is I will cover the multi-messenger astrophysics search landscape. So from the data perspective, I will cover some of the history of these NMA searches, again with the GW Data Analysis Center, search methodologies, the ingredients of an MMA search. We need to have detector data for each messenger. We need to understand the detector's behavior. We need to have a source model. I will discuss additionally offline and of course the online real-time low latency searches, possibilities for early warning. I will say a tiny bit about that. And of course we do need a statistical framework to interpret our results. Interpret if we see something interesting. Is it a real multi-messenger event, or it's a chance coincidence of unrelated events or two background events, etc., etc. The subthreshold event lists are proliferating, they're coming in line, becoming available. The statistical interpretation is incredibly important. I will certainly talk quite a bit about beyond two messenger searches. No detection of that type has been observed so far, and some outlook for the future. I actually wrote a little article into the LIGO magazine a few years ago on the early years of the multi-messenger effort in LIGO, since we have been, the Columbia group have been on the forefront of these topics since the early 2000s. If you're interested, please read it. There are little stories in there about how we were thinking originally, but I will also tell you a tiny bit about what was needed, what was important. Why do I think we are here? That actually we made some at once multi-messenger detection with using gravitational wave data, and what was the roadmap to get here where we are. So one of the first things which happened in LIGO, it joins news, back in early 2000, supernovae were themed as and they are still interesting sources, but we know that the rates are not very, very high. But we joined news as a first step, joined GCN, getting triggers from GRBs, We of course were expecting a GRB counterpart from the very beginning. And the other thing which was also important to start a network data analysis server. So combining the different detectors data, even pulling Virgo data together was very important because we are gonna, in order to have multi-messenger astrophysics, we need joint localization, we need multiple detectors. All right, so this is just a key point on our most interesting source, which is the neutron star containing binary merger system. And you know, back from our knowledge in 2013 or so, so before the first detection, what was the landscape for these type of sources, and you know what we are seeing since then. We had one very major event of a binary neutron star merger, on which we have seen counterparts. We had a few other observations. We also had NSBH observations, and you know, we are getting some information which is discussed here, but of course not everything is measured with our current sensitivities. You know, especially we are not capable of finding signals, you know, over a few kilohertz range and so on. So some of those even above you know, the 2 to 4 kilohertz ranges is, and also ringtone types is searching, and you know, we are seeing some interesting things, but you know, a lot of the things we will take a bit more and better detectors. So I'm moving forward because this was actually the neutron star containing systems was definitely our motivation for actually establishing these searches for gravitational waves in the LIGO data coincident with gamma ray burst. We knew about the short gamma ray burst. We knew that they may be associated with binary mergers. And so LIGO started to do basically a search in data itself around gamma ray burst events which were observed, and we received these information through satellites. So there were a few interesting observations, like the one on the figure on the right side, which shows actually shows Andromeda. This is about GRB 070201. This was actually one of those interesting events in the initial LIGO era, because because the localization of this GRB coincided this very close by galaxy. So even during the initial LIGO era, we could have seen a binary merger from Andromeda, and the search gave an odd result, which actually contributed to the interpretation of this GRB as in extragalactic SGR hyperfed, the first one of such. So, and of course, by now we do have one very well-known detection. So, multi-messenger searches for GWs with LIGO also happened the other way. We started the EM follow-up program. And this is not very well known, but back in 2007, summer 2007, LIGO was running, that was S-Force, the Force Science run. We had, Virgo wasn't joining yet. We had 2 detectors data we could triangulate, of course, using the 2 detectors. And we knew what is our reach, so we were using a galaxy catalog and looked at trigger times, and we actually started to point telescopes. We had to do this, you know, physicists, gravitational wave physicists, and not an astronomer by training. And we had students who actually went to MDN and also to SWOP and pointed the telescopes into direction of closer galaxies, which coincided with our information of just triggers. You know, these were like not very significant, but there's always some events which are on top of the trigger list. And we did this in fairly short time scale, fairly low latency And we actually published a little paper on this back in 2008. And this was an amazing ammunition. It was an ammunition to go and find partners who would follow up, astronomer partners who would follow up gravitational wave events from future science runs. So back in 2010, finally, we actually did have our first EM follow-up program. In back then, it was already LIGO Virgo, and we were providing joint localization, and we had order of 10 partners or so. But I think without this pilot program, this would not have happened. And just let me say one more thing about this, that by the time the first observation run of advanced LIGO started in 2015, we had 70 partners. So, the interest really became much larger. And just the sweetness is that SWOPE was one of the telescope, actually the first one which was observing the GW170817 optical counterparts. So it's just a nice coincidence, but I love to mention this. Okay, another thing was needed, and theory is important. We have been running telecom. These were called externally triggered searches telecom, that everything multi-messenger was discussed in LIGO. We had guest lecturers. So one of them was Brian Metzger, and his work really contributed to not just our understanding that this can work, the EM follow-up program work, but also into convincing the other astronomers. The fact that you have a long time, days, a week to follow up a binary merger event and make observation and hopefully see counterpart with an optical telescope is really changed everything. So an input from the theory can really guide the observation on many different ways, and this was really important in our field. Okay. I'm moving on to multi-messenger approaches, and I sort of pointed out a few of them, talking about about our history, how we got to this point where we are. So the first one was exit strategy. So we are taking satellite data, for example, the GRV satellite. So the flow of trigger information, we receive the trigger, and then we are running the gravitational wave search. We analyze the strain data which we have available. So, but in this case, there is no pressure. We can go back and analyze the collected data later and so on. This is sort of the easy way to do the searches. These things still happen. It's not like everything needs to be online. The next approach I also mentioned is the follow-up strategy. So for this, well, if we want telescope to follow up and we want to really have results out of these observations, they need to know both that an event happened, they need points. So this needs to be done in terms of the gravitational wave data in low latency. So we needed to develop a low latency pipeline, which was ready in 2010 for the S6 science run. It can provide quick localization. It can even provide subthreshold triggers list, and which we did in 2010. We were sending out triggers to our partners, which were obviously not detections, but triggers which are of higher to noise ratio and seem to have some possibility of maybe being astrophysical. A large field of view is, of course, useful on the follow-up telescope side. Okay, I'm moving on because there is a third method to search for multi-messenger events. And there are detectors, and it's not just gravitational waves, specifically the high energy neutrino detectors such as IceCube and our neutrino detectors as well, which see the whole sky continuously. And not only see the see the sky continuously, they're taking data with a tremendous uptime. So that actually brings us to the third type of multi-messenger approach, which because I am working on mostly on the GW hand search since 2006, since we established it, and this is the joint search strategy. And because the data is coming in from both detectors, it can contain, of course, high significant events on gravitational wave detections. Now we have, high significant neutrinos, we have neutrino detections with localization, we have timing information, etc. But we also have the subthreshold list from both detectors, and we can combine this. And if we find, even if from the subthreshold list, using the subthreshold events, we can still find events possibly which rise above the threshold to send an alert to the EM community and let them know about significant overlaps. And we have been doing that, as you can see. So the basic glossary of multi-messenger approaches, you see all the three here. The joint search strategy, it makes sense to do it in low latency. So you will hear about a development which we have been doing, which is called LLAMA, low latency algorithm for multi-messenger astrophysics. It takes gravitational wave and high energy neutrino detector data. We can add the GRB detectors as well. I will mention a little bit about that, and send triggers to the astronomy community to follow up. In terms of the GW hand, the high energy neutrino localization is of course much better than what we get from the gravitational wave triggers. So let me go into these two famous MMA events with our new messengers, gravitational waves and high energy neutrinos, and say a little bit about similarities and differences, because both of these new messengers and how we analyze them actually point to where we need to go in the future. So similarities, we do have significant events both in gravitational wave detector data and of course high energy neutrino data. We have high SNR and high P astrophysically significant events in the gravitational wave data. We are actually finding very high energy neutrinos, even PeV scale. Many hundreds of TeVs are already very exciting, and we have a good number of observations from IceCube on a regular week or once a week, every 2-week basis. So even the rates are somewhat similar. The localization from both detectors come available in low latency in real time. So we do have in both from both detector, both collaborations, to a method to disseminate alerts, and we tested these, and people are reacting to that, and there is a sizable and experienced EM follow-up community, so who are willing to receive the alerts, and they were willing to receive the alerts even when we told them that they may be retracting. This is very important for making future observations in MMA, to have all these ingredients coming together. There are some differences between these two events and the two detectors. The gravitational wave messenger has extra attributes. Usually what I love to say, gravitational waves, at least when we observe a CBC event, they talk to us. It's not just in event time, and it's not just the localization. We learn about the source type. We know it's a binary merger. We know the masses. We have influence on spins, eccentricity, and so on. And of course, we have a distance, right? That's important as well in interpreting the analysis results. The neutrinos, as I mentioned, provide more confined localization but than the gravitational wave events, but that richness, just because it's a neutrino, right? The only thing what we know, its flavor, its energy, and of course its direction, where it came from. So we don't have this kind of extra source information, and in terms of how we analyze it, it's different. So the inference at the end needs to be made on the MMA association for both the gravitational wave results and also the neutrino results. And there were these two important events, the GW1708-17, and just because we had the richness of the gravitational wave data, and then we got what we were expecting in terms of the GRD coincident event, GRD 1708-17A, and also even the optical counterparts. Just there was a lot of new and interesting things, but in general they were showing up as we were expecting, even though there were details which were unexpected. So nobody ever questions, did we make a right inference? Are these really related? Because it was like nearly obvious. On the side of the IceCube 1709-22A event, there is an inference on the MME association. So it was a high energy event, the IceCube event, a track event from IceCube, and it was actually associated with a flaring blazar. And we have a 3 sigma association. We have to quantify it. That's the way we can talk about it. And that's what it is. It's a 3 sigma MMA event. Okay. And this is a bit different how we are interpreting it. Okay. So you have seen this slide many times. This is, of course, in that MMA paper together of the LV detectors and the gasoline of our observing partners who have worked with us and seen something. Okay, so this was just talking for itself, that it's there, it's detected. There's no way it even fits what we expected from models. The IceCube event is here, the track event you can see, and of course there were many observations, and as I mentioned, this is the 3 sigma level associated with the blazar. Observations were coming from Swift, Fermi. There is the source name, the XS 0506+056 flaring blazar. Magic made detections as well, and even Veritas did work on this as well. So there's a lot of richness here at the 3 sigma level. Okay. So I'm going to move on to the missing combinations, since this is my high interest in MMA right now, and certainly the type of MMA search I have spent most of my time on since 2006. And this missing combination is the gravitational wave and the particle messengers speaking neutrinos. Now, of course, there is one, and this is a bit of a side note, this slide, there is one obvious which we are waiting for, which is the supernova case, and we know it since 1987. And this was actually an MMA event, right? Because there were neutrinos observed, and of course there was the optical counterpart as well. So we know that such an event can happen again. We do have, since 1987, later on SNOOS was formed. We have an amazing alerting mechanism. The neutrino detectors are combining efforts and sending a joint alert out. But of course, we have basically Poissonianly rare stuff, okay? And I'm not gonna bet on it that this is gonna, and none of us would bet on it that this is gonna happen, and we're gonna make a detection of a supernova with the current sensitivities of our important detectors and certainly the gravitational wave detectors. So on the gravitational wave side and actually the EM side also, this is likely a typical extra type of search. And that's what we need to expect. We're gonna get this news alert and everybody's gonna jump on it, and we're gonna be able to analyze the detector results for a long time because it's recorded and taken. Okay. So to ensure the detection of gravitational waves from core collapse, so for the gravitational wave detection, we really need to build the new detectors. So the 3G detectors will have much better capabilities, both the Einstein telescope and the Cosmic Explorer side. And this is actually one of the key points why I and many of us in GW Science are excited about the third generation detector. We really need this, and then we will have this really long-awaited detection of supernovae. The current sensitivities for gravitational waves from a supernova is not necessarily reaching the full galaxy. It's not that likely that we would see the gravitational waves from a supernova, even if we get lucky because the universe is kind to us and we have a galactic event. But of course, it's going to be tremendous in terms of limiting a lot of the source models, and maybe we will be lucky that it's close enough. Okay, so going back to the high energy neutrino search with the gravitational waves, this is a missing combination, and this is my favorite example. So I'm gonna talk to you in the next few minutes from the GW-HAN analysis case direction and how we are doing it, but also give a bit larger picture which can actually be generalized to other multi-messenger searches. But why GW-HAN is a good search example? Why do we need to do it? Well, we have the data, right? We have these two amazing detectors, plus KM3net is coming up as well. So it's not just the LVK detectors, plus IceCube KM3net is coming up. Significant uptime. They have, they are both watching the full sky. We don't know whether there are joint sources. There could be, and you know, I don't have a reason not to expect that neutrinos are not emitted by BNS merger. They should be. Of course, the question is that detectable with the current sensitivities of the detectors? And actually, our search is limited by IceCube sensitivity at the moment. So, if we did a significant event above a given threshold, we decide latest our threshold level was 1%, then we are sending an alert to the EM community of these joint candidates. And of course, if they, you know, they may not have much else to do at the end. We haven't found anything anything significant yet. So at the moment, we are setting a limit on the population of joint emitters. And there are several examples for that. And because I was mentioning GW170817, this is an example of the joint localizations, not just using IceCube, Antares, and actually OJ's ultra high energy neutrino data as well. Okay, so the history, just where this is coming from, this GW-HAN search. So it's coming from Pupin 1009, that's an office at Columbia University. When we got together with Chad Finley, who's an Ice Cube, and Marka, and came up with the idea, put in a very quick request to present the poster at one of the meetings, and that's the way it started. A very quick backing of the envelope calculation. We started to develop search method, which had several different versions, and just where we were in those initial LIGO era, this is not showing, but the neutrinos were only in the northern sky, that we were only considering the ongoing the neutrinos from the northern sky. And then even on the LIGO side, IceCube didn't join us yet, so we were thinking about 2 detected data, and we were triangulating just using a circle in the sky. So of course we have a lot more and better position reconstruction methods since then, but this is the way it started, and it evolved to a major analysis in both collaborations. And we actually got together at the beginning and involved some theorists, and we built a team for developing the methods and did a few early publications which are still driving our data analysis. And then, of course, there are lots of observational papers since then for every major gravitational wave event detected since then, and events related to the catalogs and etc. And lots of GCNs. GCNs are my favorite publications in a sense, because that sort of, they can point to the future. Maybe we are really going to have some counterpart example. So based on the gravitational wave high energy neutrino example, what are the ingredients of an MMA search? Well, the detector data, of course, for each messenger. The obvious thing which is needed for a multi-messenger search is the time of the transient and the localization of the transient in both detectors. We need to find the spatial and temporal overlap. That's the way it starts. Of course, there are additional attributes of the data. I mentioned how many attributes the gravitational wave event has. Of course, we can interpret its astrophysical probability or signal to noise ratio, and the signal to noise ratio of the gravitational wave itself. We need to interpret it in comparison with the detector's normal behavior. So, for example, we need to know the noise trigger rate. So if we have an event, is it how likely that it is astrophysical? On the neutrino side, the main part in interpretation is coming from the neutrino energy itself, which was detected. And that's very important. And again comes the fact that we really need to understand our detector's behavior. For example, IceCube has a very highly declination-dependent energy sensitivity. So a detected neutrino energy at different declination can have very different interpretation in terms of its signal. So we need to understand our detectors. That's very important. So additional ingredient of the MMA search, and here comes the source model. This is where it's nice to have input from the community who understand the sources or have ideas of joint sources, and give us input which can serve and help our searches or help us in terms of interpreting our results. So one of the important part of the model is a search time window, right? So we can assume a search time window. We can even model what is the ideal search time window if we want to have an X3 sigma or 5 sigma detection. Obviously, you can run a lot of simulation, and that can guide your detection probability, can guide your search window. Is that the right thing to do? Well, when you have nothing to start from, maybe that's what some analysis could do. Generally, we are still expecting some sort of a source, and I will show you our GWN source model, stand window, and where it was coming from. But this is important. This is actually one of the most important parts, ingredients of the search, which comes from an assumed model. And even if you don't have a model, it becomes a model. Whatever time window we ended up choosing, it becomes the model in which we are interpreting our result. So, of course, I mentioned that the gravitational wave data in terms of the CDC interpretation has all this richness about the source. So that is amazing. In some searches, this can be used. There are examples for that. The GWN search, we use the fact that it's a binary neutron star or a binary black hole. So we use the source type in our interpretation. If there is no model, and I already mentioned a few words about that, we are still going to have a model, which is the time window. But in terms of if there is no physical model, we just say there is some type of source out there which can emit both gravitational wave and high energy neutrinos, then the question of interpreting our result is the following: how background-like each trigger event is. So again, goes back, you are doing data analysis, but you need to do, you need to understand your detector's normal behavior. This is true for every messenger you're working. So of course, then there are the possibilities that the observations guide the source model for the search, or of course, that I mentioned, source model can enable to interpret the data from the other messengers. So let me show you an example when observation can guide a search. This is not GWN, so it's a sidetrack for this one slide, but there's an ongoing search for gravitational waves coinciding with soft gamma repeater events. This is back from the initial LIGO data. We spent a lot of time on it back then. At the moment, it's an ongoing and very productive search. There are many papers and beyond those which I am listing here, which were coming out from our group in LIGO from 01, 02, 03, and so on. So why I say that this is an EM observation guides the gravitational wave search. So it's not just a regular trigger search. We have used, especially the situation when we're looking at this pulsating tail of the soft gamma repeaters hyperflare, and the pulsating tail had a very large richness in terms of information, which was a frequency regime accessible to LIGO, or at least its multiples were accessible to LIGO, and also some information on the timing of the event as well. So the length of the search window was determined by this observation, and the frequency regime that we were looking for gravitational wave emission was determined by the electromagnetic oscillation. This was a choice we made, having nothing better, but why not try to guide our search and keeps resulting in upper limits on all these soft gamma repeater flares. But this is an example for such observation, when such search when the observation can guide the gravitation waves. Okay, I'm going back to the ingredients of the MMA search and start to discuss the search inputs. So on the gravitational wave search side, obviously we do have a sky map. We have a distance. That's very nice in your gravitational wave event. In the CDC interpretation, we have a distance. We have the SNR or P-Astro. We have the time of the event. And as I mentioned, the neutrino side, we have obviously the position reconstruction, the energy time, and of course, how well we can find the position itself, the uncertainty around the position. So I showed a few simulated joint events, when we have 1, 2 versus 3 detector data and regular, sort of typical, in this case, ice cube neutrino rates within our time window, which is 1,000 seconds. I'm gonna get to that. So these are the search inputs, and we can combine, obviously, the locally temporal. We can create a list of temporally and spatially overlapping neutrinos. And in this case, neutrino number 1, which on the first top one case is not significant, but that ends up being the most significant if we add all these factors. So beyond that, there are the search parameters. As I mentioned, we really need to understand our detector data. One of that is that if we have a GW trigger, it has a given SNR. How does it compare to the detector backgrounds? Then you can figure this out from time slides in the gravitational wave detector data. So basically, if we use, for example, 2 detectors, LIGO, Hanford, and Livingstone, the max time difference is 10 milliseconds. As soon as I am creating time slides that I move one of the detectors data by greater than 10 milliseconds, then I have a non-physical combined data on which we can do an analysis, and from this time slides we can actually find background events, right? And we can compare this. This is a generic page. Of course, in neutrinos, we do have a background neutrino trigger list with their energies, declination dependent, etc. We can compare to that. We know the ice cube effective area, their integration bonds, empirical constants, etc. So, and then there is the fact, what is the source? So we need to have an assumption on the source. Of course, there is the time of the relevant significant, relevant astrophysical event. Is that the source distributed in the universe uniformly? We are assuming in our gravitational wave search uniform distribution. And then, of course, we are assuming something about the energetics of this source. I mean, the emission in gravitational waves and the emission in neutrinos. So we are using a log uniform distribution for the source engine for both GWs and hands. Okay. Search time window. I said this is actually incredibly important because it actually constrains our analysis. We are not looking for anything which is outside of this time window. So if something is beyond the bonds here, we are never going to find it. We are not searching for that. The current time window for the GW hand search is a 1,000 second window, minus 500 to plus 500 around the gravitational wave trigger. And this is coming from a fairly old study we did back in 2011 or so. And we were using the expected association between gamma ray bursts and southern gravitational waves, but also gamma ray bursts as sources for high energy neutrinos. We looked at a good chunk of data on precursors because that indicates activity before the onset of the GRB, and we had this limit on this 250-second limit on GRB precursors, which we included in this time window analysis, and gave this conclusion that this minus 500 to plus 500 second is something which makes sense for this search. We keep using this, but if people have comments and additional suggestions, we are happy to receive. Receive no, but we are testing for 04. Everybody is using the minus 500 to plus 500 seconds and code reviews, etc. This is not gonna change. 404. It can change beyond that if others have more opinion, and I'm very happy to receive comments and ideas and etc. I think it's conservative enough, at least for transient, immediate transient emission. So the analysis can be done offline, right? So I'm showing a few results for the IceCube search. On the left side, there is 91 gravitational waves from O1, O2, and O3. We analyze all the confirmed events which are in the catalogs, and of course we do have as a final results we give neutrino emission upper limits for each of the gravitational wave catalog. Of course, we analyze GW170817, and this is just on the left side. On the bottom is actually analysis from online. So our data analysis was running online in O2, and we could provide, and we had partners, right? We actually provided them information about coincident neutrinos, but of course, as the sky map shrunk, I don't know whether you remember famously, we only had LHO data first, and the LLO data had that crazy glitch, so we didn't know much about it. So as the sky map shrank, of course, all of our events, neutrinos became, not coincident. And then we did an offline analysis which combined all the information from every detector, or most of the neutrino, high energy neutrino detectors, for which the data was available. So this is actually a joint paper between IceCube, Antares, OJ, LIGO, and Virgo, and the interpretation of the fluences, neutrino fluences, with several different models. One of them includes the model for a longer term model, and actually the event at obviously the 40 megaparsec and right at the location of the electromagnetic counterpart. That's important. So not within the full gravitational wave sky map, but if we have an electromagnetic counterpart, we can do a deeper search, which is a longer term search for a counterpart in neutrinos. So that means it's a longer term model. Longer term. Okay. So online search. So low latency GWHAN search, as I mentioned, has been ongoing since the second observation run of LIGO Virgo. We can identify the candidate events rapidly in both detectors. We can combine them, and we can actually basically send an alert to the EM follow-up community. So this is done incredibly fast in terms of seconds. Our limitation is more on the waiting the 500 seconds for collecting all the neutrinos. Yes. So we are assuming, obviously, that the compact object observed by LIGO Virgo Cagra is also able to emit neutrinos, high energy neutrinos. So, of course, these low latency searches can be also done based on signals or candidates that could not be individually established as discoveries. So we can have a joint significance of an MMA candidate that can rise above the threshold. So actually this gives rise that this analysis is happening in a subthreshold way. As I mentioned in an earlier graph, and I was showing the joint search strategy, it's not just we have a confirmed gravitational wave event triggers the neutrino search, or the other way around. We can actually combine subthreshold lists from those detectors. Okay. So, but if we are doing this, we need to treat the significance, the joint significance of the MMA event proper. And that will be a key point in a few minutes. So, but in order to have this search, we need a pipeline. This graph shows the O3 era pipeline and how it interacts with the other partners we have. So the light blue is called Llama, our low latency algorithm for multi-messenger astrophysics. This is the pipeline which was developed at Columbia. It was spearheaded by graduate student Stefan Countryman on the pipeline plumbing side. The statistics side, it was spearheaded by Dor Veska, also from the graduate student. And we of course are receiving triggers from LIGO Virgo. There are lots of terminology, expressions here, which obviously those who are involved know. If you're a theorist, it's not that important, but basically we are receiving events from LIGO Virgo through GCN, because that's the way public events become available, but we can also receive the sub-threshold list through internal means. We can also go and fetch the IceCube data, which are within our time window. And then finally, when we made this combination, create joint sky maps and do joint significance calculation, and then go back and tell IceCube, this is what we have seen. Can we send this neutrino information out? And if yes, of course, we're sending an alert, which we have many of them in GCN. During those. So this is the time scale, and what is important here is that actually the major part of our time scale is the plus 500-second part of the time window. So of course, IceCube has some time to move the detected data from the South Pole up to north, up to Wisconsin, Madison. That's order of a minute. And then as soon as we have that, we can actually analyze the and give a joint significance in a matter of 10 seconds. This is a typical example, and this is what is the plan for O4 as well. Okay, since I'm mentioning O4, and some of you may be interested in what is coming. This is probably getting around the last moment when you can start giving some input as an observational person, or maybe even as a theorist, to the LDK. So we are going to start running in March of 2023, so a few months now. Lots of preparations are ongoing, and including changes to the low latency alert system. And in terms of what we will give and provide, there will be some minor changes compared to how we were interpreting EM Bright at PSO. This sky map will be a somewhat different type, although we had this available previously with the multi-order sky map, so it takes time to get used to using that. What is important, no more of that richness which I mentioned, and you see in the catalog data that will not be provided according to current plans, real time, online. So no masses, spins, eccentricities will be given, but you will have the classification, BBH, NSBH, BNS, no mass gap. But this is what will happen if you need, because you have an amazing model, and I know some folks in the community out there who have some models where they would love to know whether is that gravitational wave event, which was just detected and announced as an open public alert, is that coming from very high mass BBH source or not. There are folks who are really interested in that because their follow-up requires a high mass model, because, for example, that's more likely to be associated with an AGN, an active galactic nucleus, where we have, and maybe a BBH happening in the disk. Can we have some electromagnetic counterparts? Some people think there could be. That's the probably the best way to have some matter around the BDH event. So if somebody is interested in following them up, obviously, that's an amazing information that will not be planned to send out, so no message will be given. Okay. So other things that will be changing is we are gonna have actually continuous data streaming through some new streaming methods, especially in LIGO. It's gonna be through something called SEMA, Scalable Cyber Infrastructure for the Multi-Messenger Physics. This is, I am actually part of it, SEMA itself. So you will have to be receiving, or possibly you could be receiving your triggers through SEMA, but there will be a GCM, I guess, type of event output as well. So one more thing which may be interesting, and and there is a tremendous effort ongoing about that. It's called early warning. So if you have a binary neutron star analysis and we are starting to see an event, you could see from the GW170817 example, you see the chirp, and that chirp shows up tens of seconds, maybe up to 100 seconds before the event, and we start to collect the SNR. It shows up in the data. So actually, LVK can do the analysis on a way that even before the merger, we know something is happening. We can alert telescopes to get ready, and we can give a preliminary alert with not the final localization without even knowing that the merger finished. Some localization, and at the end, after the merger happened, we can have a more refined localization. This is incredibly difficult to do, and of course, the especially SWIFT is one of the main targets. They need to react as quickly as well. That this would make sense. There was a lot of development on the SWIFT side that they would be able to actually react also much quicker than their usual slowing times. There was lots of changes, and they did basically as much as they can do with the telescope, which has been there for what is it, 2 decades or so. Yeah. So that's exciting and interesting, which is ongoing and coming. And we just need to have the close by event, which gives us such a high SNR that we're going to see it 100 seconds or more ahead of time. Okay, so beyond these, what we also need for an MMA analysis is a statistical framework. So the statistical framework in Llama, the pipeline which we developed is basically using the signal hypothesis and the null hypothesis. Signal hypothesis is, of course, we have a gravitational waves and at least one neutrino signal coming from the same source. The null hypothesis is that they are both backgrounds. There is the chance coincidence hypothesis. This is very important, that we need to have the chance coincidence that only one of them is a signal, the other is background, and etc. And of course there is a negligible contribution which we are not taking into account, that both signals are not background, but they come from different sources. Like, for example, the gravitational wave emitter is behind the neutrino emitter, right, from the more or less the same localization but behind in distance, and or vice versa. Okay. Of course, the question is what we have seen, because we can always throw, CPUs and run an analysis on anything. We need to tell that is this a real event or not. So we need a statistical inference. We are doing a Bayesian search. We are assuming models, as I said. We are calculating the odds ratio, but at the end, working in two communities, we also not just have to adopt. I think we are now convinced, and this is the right way to do our analysis, is that we are using the the odds ratio as a test statistic. So LIGO, Virgo, Cogra, the gravitational wave field, data analysis field is very Bayesian favored. So we have, for example, as I mentioned, we have the CDC model. We are running our analysis. We have a lot of assumptions about the source. The neutrino, as I mentioned, they don't talk to us. It's just the energy and the localization. So they always find usually likely ratio used as a test statistic. So it's a frequency test mindset. So we are using the best what we can from a model on the gravitational wave side, and of course also adding the information on the neutrino side, and we are finding an odds ratio using this Bayesian model, and we use this odds ratio as a test statistics, and then we are doing a lot of simulation. We are creating a background distribution of simulated joint events, and then we are comparing any candidate joint signal, joint MMA candidate to this background distribution, which we got from simulations, and basically determine a p-value on a frequency manner. Okay, so putting it all together, we of course need to figure out how likely a joint event belongs to the background, how likely it is a chance coincidence, like we can have real neutrinos with background GWs, or vice versa, real GWs with background neutrinos. We can calculate the chance coincidence likelihood. And of course, what is the signal likelihood? We need to calculate the spatial overlap between the neutrino and the gravitational wave. Localization, we combine
I'm sorry, Zsuzsa. I want to ask, how many slides do you have? Because we've been over an hour.
Sorry. You see, I am not seeing the chat. Sorry. I have probably. I have a few slides. I will finish quickly. Okay. Thank you.
Okay. Thank you.
You should have told me earlier.
I sent you some messages, but you are.
Yeah, no, I don't see it. I don't see it. Apologies. Thank you, but thank you for sending it though. Okay, so we are combining this, and we are finding results ratios. Okay, and I mentioned already we are doing. We have a p-value, and if it's above a given threshold, for example, for sending a trigger out online, then we send. Then we are sending the GCN out, and we have done this many times during those three. And otherwise, we set an upper limit. There are lots of papers which you can read, and very important for the topic, but obviously, I'm not gonna get more into this. So I'm gonna skip this slide, though it's very important in some sense. We sent a few alerts, so this is one example from 03, and we actually even followed this up with Swift, so there is a paper which you can read. So this type of MMA, we have gravitational wave and high energy neutrino joint alerts. People are responding to that. This is happening. We haven't found anything yet, but maybe what if we find something? So this goes to the B-on-2 messenger paper, which I certainly circulated before this talk. This is an example for one of the alerts which we sent out. And there is a gravitational wave high energy neutrino joint surge, this tiny neutrino there. And people started to look into that, how followed it up, right? They found something not within the 90% limit, but within the neutrino itself. And then there was even a radio follow-up after that with VLA. So our joint search actually started a new investigation, started an even newer investigation. So if there's anything significant found in here, we need to have a statistical treatment for this B-on-2 messenger cases. And because these multiple coincidences are inevitable. I mean, already because we are using sub-threshold triggers, then it's about what is the threshold we are setting. But we're going to have better quality data, results of upgrades. We're going to have new detectors, many different things. upcoming. So this will happen. And the inference for such multiple coincidences is basically a requirement. We will need to interpret any kind of candidate event statistically. So in this paper, we provide a generalized treatment for the statistical inference for the multiple coincident messengers. And of course, this is adaptable for our pipeline. So this is an example of the GRVHAN and GWKs. Actually, there are 8 important hypotheses. So if there are more than one hypothesis, I'm going to go to the next slides. Then we do not have a model independent optimal multi-messenger search. So we need to assume a model. And of course, just like previously I mentioned, we use Bayesian statistics, and we are putting all these different sub-hypotheses, which was explained on the previous slide, together, and again, we are using odds ratio as a test statistics. So the search inputs are what we have been before. For GWs, the neutrinos, and for the GRBs, it's whatever the obviously the instrument is providing, position and the uncertain time, and of course something about the energetics, duration, significance, fluence. And of course, we do have an interpretation of a common source parameter, so we are combining that. So this type of analysis can be done. It requires a lot of simulations ahead of time. So we would be able to build the background distribution and certainly do such an analysis when such an event happens. And I think what I meant to say and said several times before, this is inevitable. This will happen maybe in our next science run, or maybe it will happen with other messengers. It does not necessarily need to be gravitational wave, but other things can happen as well. So conclusion. So I really try to go to the end quickly. So just to mention, MMA searches already produced significant discoveries. They were enabled, these discoveries were enabled by decades-long pioneering work. I showed a rich history there of previous MMA searches, and we wouldn't be there if we were not doing, for example, optical follow-up back in 2007. It took an effort to get the community started in this. There are gonna be upgraded detectors already in March on the LEK side. There will be new instruments like Vero Rubin will be coming up, right? It's like a transient event factory. We're gonna have Gaussian transients observed daily, hourly in the coming decades. Each messenger will have subthreshold trigger list or real detection trigger as well, obviously, but even that will be a lot. So joint analysis of subthreshold lists is already ongoing. I'm just showing an example, which actually we did with Veritas, and Rashmi was involved with that. So this is a binary neutron star subthreshold trigger list analyzed together with Veritas. So this kind of analysis is already happening. So, and as I said before, some of the triggers are coming public immediately. This enables low latency or real-time multi-messenger searches. And we are already selling alerts to include additional observations. Then this is good. We should do this, obviously. This is why we are doing low latency. We're going to do a lot more of that, because if we are sending, for example, an alert based on 2 messenger data, maybe the 3rd messenger will have, to really make a detection, a multi-messenger detection in gravitational waves, high energy neutrinos, and EM counterparts at the same time. There will be, and there are actually new data streaming services coming. So that's data streaming. That's just, let's put all that data out. And I would like to remind you that data which is coming out is basically metadata. right? It's not the original, let's say that, strain data, original time series, which is being analyzed. You're getting to know that there is this type of trigger observed at this time. The information and data flow is so large that basically we really have the ability only to analyze the joint metadata from the different messengers. But that may lead us to make mistakes. So interpretation of any MMA candidate will require the knowledge of the detectors involved. So what I am urging is that people who work and interested in MMA searches, data researches, try to find partners from the other collaboration who are experts in the other detector data, because that would be leading to the best interpretation of a joint result. There are so many little nuances which are required from each detectors in order to interpret a joint result that really requires us to work together. So of course, as I mentioned, multiple coincidences are inevitable, and of course, this best statistical inference is for these MMA cases is a requirement. So this is what we try to do with this paper on the Beyond2 messenger, the Marka messenger search statistic paper, Vasquez et al., which I was talking in a few previous slides. So I definitely suggest you to read it. We also have a statement, there is no optimal search, just the model dependent search, as I mentioned. So input from the theory community, from a lot of you who are theorists, is incredibly important and critically needed, because our MMA discoveries are interpreted based on a source model. And I am really happy to receive any ideas, of course, on the GW plus and joint search case from theorists. But of course, I'm urging the theory community to think about any combination of MMA messengers and what their sources could be. And thank you, I'm done.
Okay, thanks very much, Zsuzsa. Are there any questions from the audience? Please just speak. Don't even have to raise your hands. We don't have so many people, so please just speak.
Zsuzsa, can you say what the event rate will be with the next upcoming run? When will you hit one per day? Are you already there, or when will that happen?
Okay, so all right, so we may have one per day. We may hit one per day in 04. So of course we are stating for the BNS range 160 to 190 megaparsec. But of course, this one per day is not for BNS, this is for the BBH event. There was a significant improvement in the low frequency sensitivity, which I have seen on latest sensitivity curve, and that really factors into seeing more, especially high mass BBHs and further out. So that one per day actually is not unrealistic.
Wow.
And of course, for the BNS, you should be interpreting our current rates. So for this, it's gonna be a handful, I would say, for neutron star containing. I'm not saying BNS necessarily, but neutron star containing events. We may be lucky enough to have an MMA event. There is a request from the follow-up community, which we received to keep running until an MMA event shows up. Well, I kind of find that a bit unrealistic. Those who involved in the sectors know the value of stopping for a year or even a few years and coming back with much higher sensitivity, because that will certainly increase the event rates tremendously, because it goes by the value.
Yeah. Okay, thanks.
You're welcome.
Zsuzsa, I had a question about the sub-thresholds. This is a project we did together.
Yeah.
For the future, for 04, I mean, there's going to be a lot more sub-threshold events, right? Or how is the criteria for what determines a sub-threshold event going to change, or is LIGO going to, what are the plans for that?
Actually, so we are discussing this, and obviously we are using this list for high energy neutrino searches as well. I don't think that the rate of creating the sky map of 2 per day will change significantly.
Mm-hmm.
404.
Okay.
Okay. So in terms of online analysis, we are using pretty much the same FARs, but this is not set yet.
Okay.
It's not fully set yet. Actually, we're going to have some discussions next week what will happen with the online analysis with the low latency.
Thank you.
Zsuzsa, with the next generation detectors, how much warning do we expect to get for binary neutron star mergers for the electromagnetic counterpart? I mean, you said that basically people are going to see it sometime before the merger in the gravitational wave.
So you mean CE and EC? Okay, Yuri, I don't think it's gonna be like amazingly much more because you cannot move the seismic wall, right? We have a crazy seismic wall, so nothing below 10 hertz, or in the very optimistic case 1 hertz, but of course that's another thing, right? Type of signal will be seen. So but if even that gain some gain at 10 hertz will help us to see that incoming event with a higher SNR, but in terms of the timing, it's at what frequency it shows up in the data. Don't expect tens of minutes, that won't be there.
Okay, but it's still probably quite. No, if 10 hertz is indeed the new benchmark, because currently I don't think LIGO is at 10 hertz.
No, we have the 10 hertz wall. We just were not very sensitive.
Right.
So yeah, 10 hertz is the benchmark, and okay, the ET low frequency has 1 point whatever hertz, or maybe I don't know 2 hertz. I don't remember. But it does have a lower frequency benchmark. C not, obviously, because that's not on the ground. So, of course, the interesting thing would be if we had something in that frequency range in space. You probably remember the SIGO, was an amazing concept, and we know there are sources there. So if somebody will be would like to spend money on a new space antenna type detector, I would definitely go for that, millihertz to hertz regime.
Zsuzsa, I also had a more technical question. You said that your detection for this multi-messenger network is Bayesian, and I was wondering how sensitive are you to the priors that you are choosing for this?
I mean, Bayesian means you're sensitive to your priors, right?
Right.
But in terms of our current sensitivity, what determines it is assuming that we're not making a stupid mistake on the source, for example, when it emits, right? It's actually dependent on IceCube sensitivity. So if you look at our source sensitivity, for example, versus declination, it shows up exactly at IceCube sensitivity. We are limited. I'm really hoping, TM3 net will come. We are going to have more data. IceCube Gen 2 will be the tremendous advancement for the GWHAN search. Until then, I can certainly hope the universe will be kind to us, but you know, I mentioned the Poissonian lock for the supernovae. We sort of understand the rate for supernovae good enough that that's easy to interpret. For the GWN case, why I'm more excited about this, because we just don't really know about some crazy type, and we keep it totally open. But
Now,
of course, you know, the binary merger is certainly doing a lot based on that model.
now for supernovae, we are sort of expecting a supernova within the next 50 years or so, right?
No, no, Yuri, we have been expecting a supernova for the last 50 years, forever. So
I know, but
tomorrow in 50 years, same.
but we have been expecting it for a long time. So wouldn't it be a great pity if it happens when all of the interferometers are down? Is there a plan to keep at least one operational?
You know that the current plan for that is keep geo operational, which is like in this case, I would say it's nice to have, but certainly not something. You know, this is something which can come from the community, and I actually think, and I agree. I mean, I know observers would love to see that we are on. On my side, I am actually in support of let's build that first generation detector and make that discovery then, because that will bring that discovery. But you know, again, we need very far reach for the high energy, or not just the regular neutrino detectors as well. So that push is also needed in terms of the MMA side.
Are there any other questions?
Can I ask one question? In terms of priors and things, when you release alerts, is that based on template fits or just threshold fits? Like, let's say the supernova profile from Theorist is all wrong. Would you miss that event? Or like you mentioned unknowns, whatever.
We do have the unknown type of burst search, and actually that is the burst search, and that's the first order search for supernovae. But of course there are, you know, people who are looking at the low frequency and also the higher frequency regime, the SASE related part, and around the 1000 hertz and etc. So there are people who are doing that. I think that's actually done offline. I'm not involved with the supernova search. The online search, because the burst searches are basically like wavelet type. So we're using a large set of wavelets with different frequency regime and next, basically like searching for signed Gaussians, but this is just the way you're doing a type of a burst combination. You can always put anything together from a set of signed Gaussians, right? So I think it's fairly comprehensive, but of course that type of burst search cannot beat, you know, if you have a good model and you're searching for exactly that model. There are some machine learning algorithms involved. Actually, I've seen and pretty nice. But the basic online one is the burst type. But again, as I said, for supernovae, this is going to be a triggered search. We need that neutrino trigger, and we can analyze the gravitational wave collected data for decades after that, because we are not going to have another one unless Poisson statistics works favorably for us.
Okay, so I think we are sort of approaching our time limit for this. So are there any last burning questions that we need to ask Zsuzsa? Okay, if there are no further questions, let's thank you, Zsuzsa, for giving a very interesting and stimulating talk. You know, clearly,
thank you so much, and
there is a lot of
input from you.
Hopefully, there will be lots of things which are happening in this field very soon.
Well, I'm sure we're going to have lots of gravitational wave detections within the next year, right? Hopefully,
Yeah,
May as
and
well.
hopefully with counterparts.
Yes. Thank you
Okay.
very much.
Thank you.
Thanks everyone for coming.
Thanks
Yeah,
for the
and see you.
invitation again. Bye.
Thanks.
See you in 2 weeks. Thank you. Bye.